Recall that the moment curvature relation for an Euler-Bernoulli beam can be written in this form. So the curvature is equal to the bending moment on the bending stiffness. And the curvature was also the first derivative of the rotation with respect to x. And if you separate the variables, we obtain the following expression. So d theta is m on ei dx. And then integrating both sides, we have an integral from theta a to theta b. And on the right, we integrate from xa to xb. And we call this the rotation at b relative to a. So that tells us that the area under the curvature diagram from a to b gives us a change in the bending rotation. Now at some distance x from point A, we can draw a tangent to the curve. So that will be perpendicular to this line. And we can also do the same at x plus dx. So this distance is dx. So we have another tangent drawn from here. That's perpendicular to this line. And therefore this angle here is equal to this angle of d theta. And this line has some length x dash. So the arc length here, dt, is equal to x dash d theta. Similar to this arc length ds being equal to the radius of curvature by d theta. Now for a small angle approximation, the deflection is much smaller and the rotations of the beam are much less than 1. So for that special case, x dash approaches the length x. So therefore we end up with the following expression. And we already saw that d theta is m on ei dx. And that's equal to dt. And if we integrate both sides of this equation, we have the integral from the tangent at A to the tangent at B. And on the right hand side, we integrate from xa to xb. So the expression on the left is the tangent at A relative to B, which gives us this length over here. And that can be used to calculate the deflection between the 2 points. Now we can simplify this integral using the definition of the centroid, which was the integral of x over an area over the integral over the area of a section. But here we're integrating over the area of a curvature diagram. So you can replace dA with m on ei dx, and also in the denominator and if you multiply through by the expression in the denominator, we can write this expression, which is this one over here, as the centroid of the area of the curvature diagram by the integral from xa to xb, and we're integrating the curvature over x. So if you evaluate the relative rotation, you'll be able to just multiply by the centroid of the area, which is convenient if the curvature diagram is linear. And that gives you the distance between the tangents. So these two equations are the ones we'll use to obtain the deflections and rotations using the moment area method. Please subscribe, like and comment to help me reach more students.